Greetings from EPG Pathshala. We already have seen the virus modules. We talked about virus, types of viruses and its signatures. Today we are going to talk about CodeRed virus. We are going to discuss about the trapdoors, how the trapdoors are created and what preventive measures should be taken to avoid these trapdoors. So I would start my discussion with an internet worm. A first internet worm was programmed by Morris and with three main objectives. He wanted to determine where it could spread, then spread the infection, then remain undiscovered and undiscoverable. What effect the internet worm had? It degraded the system performance. Worm's primary effect was resource exhaustion. Keep on occupying the resources so that after some time there are no resources, those can be allocated. Its a source code indicated that worm was supposed to check whether a target host is already infected. If it is infected, the worm would negotiate so that either the existing infection or the new infector would terminate. Because of the flaw in the code, many new copies did not terminate. As a result, an infected machine soon became burdened with many copies of the worm, all busily attempting to spread the infection. A second order effect was disconnection of many systems from the internet. System administrators separated their connection with the internet either because their machines were already infected and wanted to keep the worm's processes from looking for sites to which to spread. Their machines were not yet infected and the staff wanted to avoid this problem. And this disconnection had a third effect, that was isolation and inability to perform necessary work. The worm caused estimated 6,000 installations either to shut down or disconnect from the internet. Several hundreds of these systems were closed for a day and the estimated cost of damage ranged from $1 lakh to $97 million. This internet worm first tried to find user accounts to invade on the target machine with Unix platform. And the same way, in parallelly, the worm tried to exploit a bug in the Finger program. Finger is a program that is used to talk to another machine on Unix platform. Then it tried to find a trapdoor in the send mail header. The first security flaw was the joint user and system error. The worm tried to guess the passwords, and if the password was guessed correctly, it succeeded. Usually the Unix password files are stored in the encrypted form. The ciphertext in the file is readable by anyone. The worm encrypted various popular passwords and compared their ciphertext against what ciphertext was stored in a password file. The worm tried the account name, the owner's name, and a short list of 432 common passwords such as guest, password, help, coffee, coke, AAA. And if none of this succeeded, the worm used the dictionary file stored on the system for use by an application spelling checker. When it got a match, the worm could log into the corresponding account by presenting the plain text password. As a user, the worm could look for other machines to which the user could obtain access. That means now worm has become an active user of the machine and it is trying to find out who others it can affect. The second flaw concerned with Finger D, the program that runs continuously to respond to other computers' requests for information about system users. In this, the security flaw involved causing the input buffer to overflow and spilling into the return address stack. When a function is called, its a return address is always stored in the stack Because of this buffer overflow, the return address stack was overwritten. The finger call terminated and finger D executed instructions that had been pushed there as another part of the buffer overflow, causing the worm to be connected to a remote shell. The third flaw involved a trapdoor in the send-mail program. Program runs in the background awaiting signals from others wanting to send mail to the system. And when it received such signals, sendmail got a destination address. It verified it and then began dialog to receive the message. When running in the debugging mode, the worm caused sendmail to receive and execute a command string instead of the destination address. Now, internet worm, if it found a suitable target machine, it had to spread its infection by one of the three methods. First, to send a bootstrap loader to the target machine, and that had 99 lines of C code to be compiled and executed on the target machine. And now this bootstrap fetched the rest of the worm from the sending host machine. There was an element of good computer security or stealth built into the exchange between the host and the target. When the target bootstrap asked for the rest of the worm supplied a one-time password back to the host, and without this password, the host would immediately break the connection to the target, presumably in effort to ensure against the rogue bootstraps. Rogue bootstrap means a real administrator might develop to try to obtain a copy of the rest of the worm for subsequent analysis. The worm went to considerable lengths to prevent its discovery. Once it has got its position on the host machine, meaning that if a transmission error occurred while the rest of the worm was being fetched, the loader zeroed and then deleted all code already transferred and exited. There is another virus called CodeRed. CodeRed malicious software that propagates itself on web servers running Microsoft IIS software. CodeRed worked in a two-step infection and propagation. It overflows the buffer in the dynamic link library. The library name is idq.dll. What the CodeRed wanted to do, it wanted to reside in the server's memory. CodeRed to propagate, it checks IP address on port 80 of the PC to see if the web server is vulnerable. Now, when CodeRed was in incubation, it's the first version of CodeRed defaced the websites with the text, "Hello, welcome to http www.worm.com hacked by Chinese." Now, rest of the original CodeRed's activity were determined by the date. So now, CodeRed worked according to the date. From day 1 to 19 of the month, the worm spawned other 99 threads that scanned for other vulnerable computers starting at the same IP address. On days 20 to 27, the worm launched a distributed denial of service attack at the US website www.whitehouse.gov. A denial of service attack floods the site with large numbers of messages in an attempt to slow down or stop the site. Then finally, from day 28 to the end of the month, worm did nothing. CodeRed had several variants. The second variant was found in July 2001. Its propagation was randomized and optimized to infect servers more quickly. The third variant was injecting a Trojan horse in the target and modified software to ensure that a remote attacker could execute any command on the server. The worm also checked the year and month so that it would automatically stop propagating in October 2002. The worm rebooted the server after 24 or 48 hours, wiping itself from memory, but it left the Trojan in the place. The CodeRed looked for vulnerable personal computers, and as I told, it works with Microsoft IIS server. It tried to exploit the unchecked buffer overflow and the worm crashed Windows anti-base servers, but executed code on Windows 2000 systems. The later versions of worm to create a trapdoor, CodeRed copied %win directory, percentage that says the path of the win directory, and cmd.exe to 4 locations. The locations are inetpub, program files, inetpub, program files. So it tried to corrupt the root.exe, root.ext, root.exe, root.ext, and root.exe. CodeRed was also included its own copy of the file explorer.exe. It placed it in the C drive and D drive, so if Windows would run the malicious copy, not the original copy. This Trojan horse first ran the original untainted version of explorer.exe. It modified the system registry to disable certain protections, and then it ensured that some directories have read, write, and execute permissions. The Trojan horse had a virtual path that could be followed even when explorer.exe was not running. The Trojan horse continued to run in background, resetting the registry every 10 minutes. Thus, even if a system administrator notices the changes and undoes them, the changes are applied again. The worm created 300 to 600 threads. After that, system was forcibly rebooted, flushing the worm in memory, but leaving the backdoor and the Trojan in place. What a CodeRed do to speed up its performance? It used non-blocking sockets so that a slow connection would not slow down the rest of the threads as they scanned for a connection. So CodeRed basically worked as a Trojan horse, which is a non-threatening program but quickly takes over the system once it is executed. Trojan is not like viruses and worms. It is not self-replicating, neither it creates a copy of itself. Infection involves opening an email attachment or downloading and running a file from the internet. We want to go ahead with the discussion of Trojans. There are different types of Trojan. The first is backdoor Trojan, which is designed to circumvent authentication, giving remote access to the hacker. A Trojan ransom, also known as ransomware, can encrypt data or lock up the system until victim pays to the criminal. The Trojan spy can log your keystrokes. The Trojan mail finder can acquire email addresses from your computer's address book. Trojan Banker, which steal online banking and credit card information. We will talk about ZS Trojan. Trojan Banker is ZS, Z-board. The ZS Trojan can add extra fields to a web page with a form, like the pages one might visit when doing their online banking. Actual bank's web page and not forged site, a few extra fields to fill might not seem as suspicious to the user. These parameters may be added as security questions, and they can give criminal the needed information to gain access. ZS also was sold as a malware toolkit, enabling less experienced cyber criminals access to the technology. This GS toolkit could cost up to $10,000. Another malicious code on the web is called web bugs. A web bug is a pixel tag, or it is called clear GIF, 1x1 GIF, invisible GIF, or backend GIF. So it is a hidden image on any document that can display HTML tags such as A. Malicious code on the web bugs. load the home page for commercial.com. It is a commercial website which sells all kinds of housewares. That website had a web bug for market.com. It is a marketing and advertising firm. The bug, what it used to do, it used to place a file called a cookie on a victim system's hard drive. Cookie is nothing but a numeric identifier. It is unique to the machine and can be used to track victim surfing habits, or it can build a demographic profile. This demographic profile can be used to direct victim to retailers in whom victim may be interested. Now this webbug commercial.com, it create a link to other sites, display a banner advertisement to attract users to its partner sites, or it may offer you the content customized according to your needs. Web bugs doesn't sound malicious. What they plant is they plant numeric data but do not track personal information such as your name or address. While you are purchasing an item at commercial.com, it may ask to supply such information. Web server can capture such things as victim computer's IP address, kind of browser the victim use, victim computer monitors resolution, other web browser settings such as whether victim has enabled Java technology connection, time, previous cookies, cookie values, and other information. How these informations are useful? This information can be used to track where and when victim reads a document, what victim buying habits are, or what victim's personal information may be. The web bug can be cleverly used to review the web server's log files and determine victim's IP address, and it can open victim system to hacking via the target IP address. Targeted malicious code, another class of malicious code, is written for a particular system, for a particular application, and for a particular purpose. Targeted malicious code, we want to talk about Trapdoor. Trapdoor is an undocumented entry point to a module. While a code is being developed, the trapdoor is inserted. Usually when code is developed, there is a testing module that provide hooks by which to connect future modifications or enhancement. This trapdoor hooks might be created to allow access if the module fails in the future. Then what remedial actions can be taken? Trapdoors can allow a programmer access to a program once it is placed in production. The developer or tester might want to test the component on its own. At that point, it does not use the surrounding routines. It prepares that surrounding routines that gives the input or work with output. So a module which developer is working on would be developed as a standalone routine. It is usually necessary to write stubs and drivers. For what purpose? Stubs and drivers are the routines which are attached to the routine of the developer to inject data or to extract results. As the testing continues, these stubs and drivers are discarded because then they have to be replaced by the actual components. For example, there is a module called mode A and mode B, and there is a driver main. The stubs are sort, output, and new line. They are the stubs, that means they are temporarily developed to feed input or to take output from the routines. Now, going ahead with the trapdoors, usually developer does unit and integration testing through which they can find out the faults. When the source of a problem is not obvious, what a developer does, it tries to do the debugging. Usually through the debugging code, in the modules which are suspicious. This debugging code makes it visible what is going on as the component executes and interacts. So if you have tried to write a program, and if your program is not working, what you do is you try to insert a print statement. You try to print the variable names and variable values, what value they occupy at a certain stage. So these are called the debugging instruction because your module is not behaving the way you want it to behave. Now this extra code is showing the intermediate results of the computation, or they print out the number of each step as it executed, or they may perform some extra computations to check validity of the previous components. Now this stubs which we have written temporarily or invoking the debugging code, the programmer embeds special control sequences in the component's design to support testing. For example, if you have a text formatting system, the system might recognize the commands such as .page, .title and .skip. During testing, the programmer may have invoked the debugging code using a command with a series of parameters of the form where is equal to value. Actually, where is equal to value allows programmer to modify the values of internal program variables during execution. For the test, either to test corrections to this component or to supply value passed to the components. Command insertion is a recognized testing practice, right? We keep on putting the commands for the debugging. But if this is left after testing, these extra commands can be a problem. These undocumented control sequences that produce side effects can be used as a trapdoors. The internet worm spreads its infection using just such a debugging trapdoor in an electronic program. Trapdoor has another source which is poor error checking. When data value you enter, it is checked before it is used. What kind of check we make on the data? Its data type is correct and value is within the acceptable bounds. A component's code, if we have written a code for any component, it checks for 3 expected sequences. Out of this, if it finds one, it recognizes it as an error. Suppose a case statement to look for each of the 3 possibilities. A careless programmer may allow a failure simply to fall through the case without being flagged as an error. So if we have written a case statement with these 3 options, 1, 2 and 3, and if our input does not match with any of the 3, then a default case is executed, but the programmer does not show an error that the value is not what has been expected. The fingered flaw exploited by Morris occurs exactly that way. A C library input-output routine fails to check whether characters are left in the input buffer before returning a pointer to a supposed next character. Now, if we are talking about causes of trapdoors, the reasons are: forget to remove them, intentionally leave them in the program for testing, intentionally leave them in the program for maintenance, intentionally leave them in the program as a covert means of access to the component after it becomes an acceptable part of a production system. So we introduced a keyword saying that covert. So what is a covert channel? It is a programs that leak information. A service program containing a Trojan horse that tries to copy information from a legitimate user. Legitimate user means one who is allowed access to a spy Spy means one who is not allowed the access. The user is unaware of the Trojan horse. Covert channel means the programmer may want to develop a program that secretly communicates some of the data on which it operates. The programmer is the spy and the user is whoever runs the program. So to show you how to create a covert channel, this is the sample example. In printing, the programmer can encode the data values by varying the format of output, changing the length of line, or printing or not printing certain characters. For example, changing the word total to totals, TOTAL to TOTALS in a heading would not be noticed, but this creates a 1-bit covert channel. So absence or presence of S conveys 1 bit of information. Numeric values can be inserted in insignificant positions of the output field, and number of lines per page can be changed. Another covert channel is called storage channels because they pass information by using the presence or absence of object in the storage. A covert channel is the file lock channel. In multi-user systems, files can be locked to prevent two people from writing the file. So if operating system or database management system is allowing only one program to write a file at a time, by blocking, delaying or rejecting write requests from other programs, a covert channel can signal 1 bit of information by saying that whether the file is locked or not. So you can see the figure. If the service program asks for a file and if it is locked, it would say yes to the spy program, and if it is not locked, it would say no to the spy's program. So in this way, to signal a 1, the service program locks the file. For the interval, for 0, it does not lock. With the disk storage, the service program signals a 1 by creating an enormous file so large that it consumes most of the available disk space. What we are trying to say in this, that the service program can create a large program and occupies the space. Later on, if the spy program tries to create a large file, if it succeeds, the spy program infers that the service program did not create a large file, and so the service program is signaling a 0. Otherwise, the spy program infers a 1. So existence of a file or other resources of a particular name can be used to signal. In this way, the spy can determine the existence of a file. It cannot read by trying to create a file of the same name. To signal more than 1 bit, the service program and spy program signal 1 bit in each time interval. So you can see in the time interval 1, time interval 2 and time interval 3, a service program using a timing channel to communicate by using or not using an assigned amount of computing time. A multi-program system with 2 user processes divided time into blocks and allocates blocks of processing alternatively to one process and the other. A process is offered processing time, but if the process is waiting for another event to occur and has no processing to do, it rejects the offer. The service process either uses its block to signal 1 or rejects by signaling 0. So you can see how timing channels are allocated for the normal scheduling and for the service program communicating 1, 0, 1. 1 means service program is occupying, then it is saying 0, it does not occupy, and then 1, it is occupying. First, the service process and spice process alternating, then with the service process communicating the string 101 to the spice program. The second part of the example says the service program wants to signal 0 and the third time block is allocated to the spy program. How to identify the covert channel through the shared matrix. In the shared matrix, what it does is it signals the R can read or observe the resource, and M can set or modify, create or delete the resource. For example, the file lock channel has the matrix locked for service program in R and M, spice process R and M, confidential data service process R. So this kind of matrix is created. Look for 2 columns and 2 rows having the following pattern. This pattern identifies that 2 resources and true processes such that second process is not allowed to read the second resource. So in this module, we have checked about the CodeRed and internet worm. We have also checked how to create the trapdoors and how to create the covert channels. Thank you.